Hi there, we're going to look again at some vectors in further maths here. We've got exercise 4A. Now, we did a lot of vectors in year 12 further maths, but I suppose one of the things I want to do first of all is make sure you can remember what it was we were playing around with. So here's a starter. So I'd recommend you pause the video and see how much of this you can do. I will then show you what I think the answers are. So I'm going to pause the video now, and you should do the same. So, okay, let's have a look at this first question. It says we've got a line passing through these 2 points. Well, first of all, I want the equation of a line. Now, when you do this, you always want the direction vector. Direction vector, you take one away from the other. So I'm just going to do this quickly. 5 take away 3 is 2. Then 1 take away minus 1 is 2. 8 take away 2 is 6. Now, interestingly, that is direct. That I could use that. But actually, if you can divide them all by a number, and you can clearly see I've divided them all by 2, you should do so. It makes your sums later on easier. Now I've got my direction vector as 1, 1, 3. My vector equation on the line then is r equals any point on the line. We might as well use the first one. 3 minus 1, 2 plus, and usually you use lambda or s or t is quite common as well. 1, 1, 3. You should remember that. That's called the vector equation of the line. We now write down the Cartesian equation of the line. Well, okay, then fair enough. This basically r is another way of writing x, y, and z. So if I do that, I can just read across this top line. I get 3 plus lambda equals x. I get minus 1 plus lambda equals y. And I get 2 plus 3 lambda equals z. Now, just rearranging to get lambda in each case. So lambda equals x minus 3. Lambda equals, you can see why this is actually better doing this. If I had 2, 2, 6 there, I would have a more complicated equation here, but I haven't now because I did a bit of work with that direction vector, y plus 1. And this one, I think I do have to leave a little bit complicated. It's z equals, well, lambda equals, I don't know why I said that, lambda equals z minus 2 all divided by 3. Now, you can't do much with this other than just to say they're all equal to lambda, so they're all equal to each other. Minus 3 equals y plus 1 equals z minus 2 over 3. And although it's not very nice, that is the answer. Find the intersection of this new line, okay, with the last line in question 1. So that was this one here. Okay, now to find the point of intersection, you basically have r equal to this and r equal to that. So you set them equal to each other. So question 2, I'm going to write 3 minus 1, 2. This is my first line, plus lambda 1, 1, 3. Now I'm pleased I used lambda because my second one is actually, they've used mu already. So good job I didn't use mu, or else I'd be having to change everything. 2, 2, 9 plus mu minus 1, 1, 2. Now, the trick with this is the top line must be equal to each other. So 3 plus lambda equals 2 minus mu, nearly wrote plus, and minus 1 plus lambda equals 2 plus mu. So you can basically play around these two equations and try to solve them. And I'm just going to do it properly. You could do this on your calculator. So I get, if I add these together, I get 2 plus 2 lambda equals 4, and the mu's cancel. That's why I've done that. So move that over, I get 2 lambda equals 2, lambda equals 1. Okay, and now I've got lambda equals 1, I need to get mu. So I sub that back into, let's sub it into the bottom equation. So I've got minus 1 plus 1, well, that's 0, equals 2 plus mu. So if I just jiggle it about, I reckon mu equals minus 2. So there's my two values. Now, if they're true, then this bottom line will also work. And that's the little check you do, just make sure. So on this side, I've got 2 plus 3 lambda, 2 plus 3 lambda. And that's meant to equal 9 plus 2 mu. Let's see if I get the same answers. Lambda is 1, so that's 2 plus 3, that's 5. That's minus 2. That is 5 as well when I do that sum. So 5 equals 5. That works. The last thing which I haven't yet done is sub these values of 1 and minus 2 back into my well, either this one or this one. Doesn't really matter. I like the look of this left-hand one. So therefore, 3 plus a lambda, well, that's 4 because lambda is 1. Minus 1 plus a lambda, that's 0. 2 plus 3, that's 5. So there's my coordinate of that point. So you can see this has taken a long time because this is quite tricky maths that we've done in the past. So this is just meant to be at the moment a little reminder of what things we've done in the past. Let me just erase everything on that slide. Question 3, find the acute angle between the two lines. Well, all right, then let's go back. What did we have? We had, well, obviously we've got these two lines. I'm just checking to see if I've written it down somewhere since I rubbed it out. Yeah, it's lucky I have. So I've got my first line had a direction vector 1, 1, 3 in the end. And this is the key there. When you want the acute angle, you want the two direction vectors. So my first one is D1 is that. My second one is this line here. My direction vector here is minus 1, 1, 2. Remember, the direction vector is always the one attached to the lambda or the mu or whatever letter you've got. Now, you have to times them together. Dot product is the rule. And when you dot product them, you get 1 times by minus 1, which is minus 1. 1 times by 1, which is 1, so I'm going to plus 1. 3 times by 2 is 6, and that actually gives me 6 when I do it. But there's another way of writing D1, D2. When I dot them, it's the modulus of D1, the modulus of D2, or the magnitude, I suppose it should be, times by the cos of the angle in between. So let's just do this. The square root of this one, 1, 1, 3 makes 9. So I'm doing a bit of Pythagoras for that. So that's 9 plus 1 plus 1 is 11. Root 11 times by root 1, 1, 4 when I get that. So that's 6 cos theta. And the great thing about this, I know what the answer is. It's equal to 6. So cos theta is 6 divided by these two go over. That's root 66 when you do it. And you inverse cos it. And I've already done this answer, I think. When I've typed this into my calculator, I get 42.4 degrees. Now, interestingly, the book got slightly different. So it'd be interesting if it's me that's made the mistake or them. So you can check that for me. And then question 4, what's it say? Find a vector which is perpendicular to both of those. Oh, right, perpendicular to both of those lines. Now, you might recall, in order to get, if you want an angle perpendicular to two different vectors, in this case, we've got, what was it? Well, it's these two up here, these two direction vectors here. That's what we use. And I'm going to find, it's V1 cross V2. We use, I should read it right, D1 cross D2. And the trick is to go I, J, K, and then put the first vector down here, 1, 1, 3, and then minus 1, 1, 2. Okay, so now what do we do with this? Well, it means it's I times by 1, 1, 3, 2 as a, I'm doing it slowly so to remind you of what it is we did last year. J, you do the other four numbers, so it's 1, minus 1, 3, 2, but notice I've written minus J because it goes plus, minus, plus K times by, now K, 3, 2 disappears this time, 1 minus 1, 1, 1. So let's do those three lines. I is 2 take away 3 minus J, 2 take away a minus 3, so it's plus 3 plus K, 1 minus a minus 1 plus 1. So it's minus I minus 5J plus 2K. Right, let's just check my answers. Well, I think just about, yeah, that's my answer underneath there. If I was to zap the screen, hopefully you can see that my answers from before kind of work. So hopefully that is an introduction to what we're going to do on vectors and what we're doing in this PowerPoint. Now, I'm not going to get much time. I think this is 2 videos and there's quite a lot to go through. So I'm going to make a start now. There are basically 2 situations which we need to be able to find the vector equation from, vector equation of a plane from. Remember, vector equation of a plane is a flat surface. So this is one such flat surface. You can see it drawn here. And the idea being, if I know a point in the plane, and thereby I know a vector in the plane. This R is a vector in the plane, R. And I know a vector coming off the plane, which is at right angles to the plane. I can write r dot that vector equals, now you very often see this as r dot n equals d, some number. This is not a vector, this is a number. So r dot n equals d. R is a vector, that's the x, y, z if you like, and n is this normal coming off the plane. And we'll come back to that. That is one type of equation you see quite a lot, but write those down. The second one is, what if you've got 3 points in the plane? I've got P, Q, and R here. P, Q, and R. And essentially, you need 2 directions in the plane. So, for instance, D1, the first direction might be I find that one there. And the second one is I find that one there. That might be my 2 direction vectors within the plane, as long as I then use any old point in the plane, usually probably the P. And I can write it like this. Now, what you've got to get used to is the fact that these look completely different. But it's perfectly normal to write with vectors equations which look different but really are the same thing. That's quite normal when you do that with vector equations of the planes or lines or anything. So we have to get used to that and accept that. And to mark it, it's even worse because you have to work out which ones are the same and which ones aren't. So let's start off with this one in the few minutes we've got left of this part of the video. Find the equation of the plane containing the points A, B, and C such that this, oh right, so this is like that second example I just described, and I've written it up here. So I've got A, B, and C. So I'm going to write A, B, and again we have to just be aware that we might end up with the wrong version here. But hopefully when I did my answers many moons ago on this, I'm going to use the same logic. So I'm going to say AB is, well, I do it in that order. 1 take away 3 is -2. -1 take away the 4, it sounds like -5. And 3 take away 2, take away a -2 is +5. So that's one vector, and I'm now going to do AC, a second vector. I could do BC or anything. It doesn't have to be a particular order, but it makes sense if I do that. And let's hope that my logic was the same last time. 5 take away 3 is 2. 0 take away the 4 is -4. And 2 take away the -2 is 4. Now, I could simplify that. I'm not going to, just in case I've done the same. I just now need a point in the plane, which is probably going to be my A. So my A, if you like, is this first point, 3, 4, -2. And then I can write my vector equation as a plane as R equals that 3, 4, -2, plus some unknown lambda times my first direction vector, -2, -5, and 5, plus mu times by my second one. Again, allowing for the fact that I may well have divided them all by 2. I may well have completely used different points. Let's see what I said. I'm pleased because I didn't. I was lazy last time as well. That's exactly what I've done last time. So, second question. Find the vector equation of the plane containing the line this and this point. Well, notice, by the way, straight away I've got a point in the line. My A is -2, 1, 2. That is a point in the line in the plane. Now I've got this is a vector in the plane. So right, and so it's got to contain this line. So my first D1 equals that one there, -3, 1, 1. I just need one more direction vector and I'm done. So how about I just use this one? That's a point in the line, that's a point in the line. I don't know which one I've done actually. I could have ended up using either. But I'm going to say 4 minus that -2, which is 6. -1 minus that 1 is -2. And 2 minus the 2 is 0. So I think I can write this. And my big question is, which point did I use? It could be -2, 1, 2, plus lambda, -3, 1, 1, plus mu, 6 minus 2, 0. My suspicion is I've used that instead of that one there. But let's see what I've done. I did. Look at that. 4 minus 1, 2. It makes no odds. Again, those are both points in the plane. Both are good enough. That lambda, that mu. So look, that's the end of this part of it. I'm going to carry this on because there's lots to go through here. And I want you to now watch the second video on vectors equations of planes. Thank you.